A coding agent's performance is governed by its harness, the collection of model external components like the system prompt, tools, middleware, and memory surrounding the fixed model weights. This harness acts as a multiplier. Redesigning these components materially shifts the agent's ability to complete long-horizon tasks. The engineering constraint we face today is that the optimal harness is highly model-specific. Whenever the base model receives an update, the entire surrounding scaffolding has to be completely rebuilt. Currently, this rebuilding process is a manual craft. Human engineers have to comb through millions of tokens in raw trajectory logs, hunt for recurring failure patterns, and handwrite targeted edits to the prompts and tools. That manual workflow is too slow. It cannot keep pace with a landscape where new base models are aggressively released every few months. The raw reasoning capability of these models is now moving faster than our ability to engineer the infrastructure around them. We have to automate the harness design process. The standard industry attempt at this automation is to deploy another large language model as a self-improving optimizer, tasking it with reading the logs and rewriting the harness itself. In practice, this approach typically results in blind trial and error, where the agent's performance degrades over successive iterations. The collapse happens for three exact reasons. The optimizer is forced to navigate a heterogeneous action space of intertwined code. It gets overwhelmed by voluminous trajectory logs, and it has no mathematical way to attribute a specific task outcome to a specific edit. Agentic harness engineering, or AHE, is a framework designed to solve this exact failure state. AHE operates on a specific thesis. The bottleneck to automated evolution is a lack of observability. By providing structured context over a clear action space, a standard optimizer model can successfully drive the evolution loop. If you provide an ordinary optimizer model with structured visibility over its actions, its experiences, and its decisions, it can transition into a stable, automated evolution loop. The first problem an optimizer faces is the state space. It cannot systematically tune a monolithic block, where system prompts, tool logic, and memory functions are heavily intertwined. AHE solves this through its first architectural pillar, component observability. This requires a mechanical refactoring of the architecture. The tangled harness is decoupled into 7 distinct editable component types. Instead of hiding these components as abstract variables, they are exposed to the optimizer strictly as standalone files, complete with a tracked version history. The immediate diagnostic benefit is clarity. Every failure pattern the agent encounters now maps cleanly to one specific component class. This setup enforces a critical requirement on the optimizer. Every single proposed edit to these files must be executed as an atomic, indivisible action. Because the components are separated at the file level, any structural change the optimizer makes can be cleanly rolled back without leaving behind stray lines of code or prompt artifacts. Component observability eliminates the monolith problem. It takes an amorphous tuning task and translates it into a strictly defined, revertible action space. The next hurdle is the signal-to-noise ratio generated during long-horizon coding benchmarks. A single evaluation run of a complex coding agent produces millions of raw trajectory tokens, burying the actual cause of a failure under layers of execution logs. Feed raw logs directly to an optimizer and it loses context, suggesting fixes for problems that simply don't exist. This is addressed by the second pillar, experience observability. HA implements a distillation pipeline. Rather than passing raw text, this mechanism works by filtering raw trajectories down into a clean, layered structure of data. The final output is a drill-down corpus of root causes. By structuring the data this way, the optimizer is forced to consume actionable insights instead of drowning in log noise. The final and most dangerous obstacle is attribution. Older automated loops would keep any edit that coincided with a successful run, meaning they steadily accumulated false positives over time. To fix this, AHE introduces its third and most novel pillar, decision observability. The process starts when the optimizer proposes a specific modification to one of the teal component files. But an edit alone is no longer accepted. It must form what AHE calls a falsifiable contract. Every proposed edit is paired with a self-declared prediction of how that edit will change behavior. The edited agent passes through a processing gateway and is reevaluated on a benchmark of coding tasks to generate a numerical outcome delta. Now comes the strict verification step. The system takes the benchmark outcome delta and compares it directly against the initial AMBER prediction. If the prediction holds true and the task outcome objectively improves, the edit is permanently kept in the harness. This mandatory prediction step shifts the optimizer's behavior. It forces the agent to act like a scientist testing formal hypotheses, rather than a gambler simply throwing code at the wall. The integrity of the entire system relies on what happens during a negative outcome state, when the verification step reveals the prediction failed to improve the benchmark. When an edit fails, the system executes an automated, strict enforcement of the revert function. Because Pillar 1 isolated every component as a standalone file, the system can roll back the specific failed component at exact file granularity. It leaves zero residual code behind. Prior automated systems lacked this surgical rollback, slowly accumulating toxic edits until the agent's performance broke under the weight of false positives. The strict revert protocol is the ultimate filter. It guarantees that the agentic harness strictly accumulates mathematically verified improvements over time. To see how this strict observability loop performs in practice, we examine the headline results on the Terminal Bench 2 Pass at 1 metric. This chart shows the progression. 10 iterations of the AHE loop lifted the pass rate from 68.9% up to 77.0%. The 77% success rate surpassed the human-designed codex harness, and it achieved this while strictly holding the base model fixed across all tests. The gains isolate entirely to the harness edits. The resulting harness is also transferable. When the frozen AHE harness was applied to SWE Bench Verified across entirely different model families, it achieved the highest aggregate success metric without ever requiring any additional re-evolution. But the most revealing data comes from the component ablation study, which isolates exactly which parts of the harness drove these massive gains. This table breaks down the ablation. Look at the positive green rows. Performance gains lived entirely in structural adjustments, tools, middleware, and memory. Now look at the red row. Tuning the system prompt, relying on prose-level strategy, actually regressed performance during cross-model transfer. This signals a shift in engineering priorities. While prompt wording regresses under transfer, optimizing the factual structure of tools and middleware provides a stable, scalable path to improving agent performance. Maintaining engineering rigor also means acknowledging the architectural limits of the AHE framework. First is non-additivity. Harness components interact with each other, meaning that stacking two edits that are effective on their own does not guarantee a proportional aggregate gain. Component interference naturally caps the system ceiling. Second is regression blindness. Because the loop verifies outcomes on a one-round lag, it can only catch a harmful side effect after it degrades the next evaluation cycle. It confirms fixes reliably, but it cannot foresee regressions. Despite these limits, the overarching philosophy holds. To automate AI development, you must defeat the observability bottleneck. The future of agentic self-improvement does not rely on unchecked optimizer brilliance. It relies on enforcing the scientific method within the architecture. State a hypothesis, verify the outcome against hard data, and ruthlessly revert failure.